Recall that we determined the electric field for a charged object which had a negligible size in the context of the problem being analysed, and therefore we treated the object as a point charge, and where this charge was positive, the electric field points away from it and drops off according to the squared distance away from the charge. Now in problems where we cannot treat an object as a point charge, such as in the case of a wire with the charge distributed on it, and similarly a plate with the charge distributed over its area, then what we do is determine a differential charge. So for example, along this wire, and therefore we can write the differential electric field as follows. And then what we do is integrate this equation to determine the electric field due to the charges distributed on the entire body. So we have 1 over 4 pi by the permittivity of free space being constant, and then we integrate dq on r squared, effectively superimposing those differential electric fields. And the electric field points in the direction of the unit vector from a positive charge to a point in space where we're determining the electric field. Now for a charge distributed along a line, we can take the differential charge as the linear charge density, which is in coulombs per length, and then multiply by the differential length, for example along this wire, or dx, gives us a differential charge in coulombs. And similarly for this plate, we look at a differential area of charge, and we thereby take the areal charge density, which is in coulombs per area, and integrate over the area. So again our differential charge is in coulombs. And similarly, for a distributed charge on a three-dimensional body, we take the charge density, which is in coulombs per unit volume, and then multiply by the volume of the differential element, gives us a differential charge in coulombs. And we'll utilize symmetry to our advantage to simplify determining the electric field for a charge distribution on different bodies. And now we'll cover some examples where we apply this integral. Let's determine the electric field for an infinitely long wire at a point along the bisector. So therefore, using this differential equation to determine the electric field, we'll integrate it. So we have 1 over 4 pi by the permittivity of free space by the integral with respect to the charge. And we multiply by the unit vector from the differential charge to that point. Now due to symmetry, we only need to analyze half of this wire. So we're going to integrate from 0 to infinity, because we can see that the electric field, due to the differential charge on one side of the bisector, is going to cancel the electric field due to the differential charge along the other side of the bisector in the horizontal direction. So basically we resolve this differential electric field in the horizontal and vertical directions. So in other words, in the horizontal direction, these vectors are going to cancel, and therefore the electric field is 0. And in the vertical direction, we're integrating over 1/2 of the wire, so we have 2 multiplied by 1 on 4 pi by the permittivity of free space, and we integrate from 0 to infinity. And remember that the linear charge density can be used to rewrite the differential charge in terms of the length of the wire, so that will be the linear charge density dx, and that's divided by r squared, which is x squared plus y squared. So this is the origin that we're taking. So we can write r squared as x squared plus y squared. And remember that the electric field was resolved in the vertical direction. So these angles here are all equal. So to get the vertical component, we multiply by cosine theta, which is y on r. So note that r is the square root of x squared plus y squared. And now we can simplify this integral as 1 over 2 pi epsilon naught. And the linear charge density and y are constant, so we're going to take them out of the integral. So we have dx on x squared plus y squared to the power of 3 on 2 in the denominator. And now we can use trig substitution to evaluate this integral. So note that tan theta is x on y, so x is y tan theta, and therefore dx is y sec squared theta d theta. So note that y is always constant, being the vertical distance from the origin to the point where we're determining the electric field. So now if we make those substitutions, we have dx is y, which we'll take out of the integral. We have sec squared theta d theta. And x squared is y squared by tan squared theta, which will factor out. So we have plus 1, and that's to the power of 3 on 2. So note that our integral was with respect to x previously. So as we can see, as x approaches infinity, this line gets flatter and flatter. So theta gets shallower and shallower and approaches pi on 2. So have a think about this. So therefore we integrate from 0 to pi on 2 when we're integrating with respect to theta. So let's keep simplifying this integral. So we have y squared to the 3 on 2, which is y cubed in a denominator. So therefore y squared on y cubed will cancel. So we get a y in the denominator. And in the numerator we have sec squared theta. And we're left with 1 plus tan squared theta. So if we recall our trig identity, and dividing this by cosine squared theta, so what we get is sec squared theta to the power of 3 on 2, which is sec cubed theta. So therefore this becomes 1 over sec theta, or cosine theta. So if we integrate this, this becomes sine theta, evaluated from 0 to pi on 2. So the integral evaluates to 1. And therefore, our electric field has a magnitude of lambda on 2 pi by the permittivity of free space by y. So remember, with a point charge, the strength of the electric field was inversely proportional to the squared distance. But now with an infinite wire, it's inversely proportional to the vertical distance from the wire. And the direction of this electric field is in the vertical direction. So recalling the symmetry of the problem. Recall the integral we derived for the electric field along the bisector of an infinite wire. But in this case we have a finite wire which has a length L. So we integrate from x equals 0 to x equals L on 2 due to symmetry, similar to an infinite wire. So the charge on both sides result in the horizontal components of the electric field cancelling each other out. So due to symmetry, the net electric field is going to act vertically. So in the case where the length of the wire approached infinity, we had our angle theta approach pi on 2. But in our case here, our wire has a finite length. So therefore we can use trigonometry where tan theta is equal to L on 2 being the opposite edge on the adjacent edge being y. So the distance from the origin to the point where we want to find the electric field along that bisector. So taking the arctan, we obtain theta is the arctan of L on 2y. So if we evaluate this integral, it'll evaluate the sine theta from theta is 0 to the arctan of L on 2y. So therefore we're going to get the sine of an arctan. So if we suppose this here is some general value being alpha, then using trigonometry you can simplify this to alpha on the square root of 1 plus alpha squared. So therefore the magnitude of our electric field can be written as follows. So we have alpha is L on 2y over the square root of 1 plus L on 2y squared. So we can put 2y in the denominator, which gives 4y squared. And we have the charge density by the length of the wire in the numerator, which is a net charge on that wire. So effectively, if y is much larger than the length of the wire, then this term here disappears. And the square root evaluates to 1. And we end up with the finite wire behaving like a point charge. And note that the direction of this electric field points upwards due to symmetry. Let's determine the electric field of a thin ring along its axes. So here we look at the plan view to visualize our charge distribution along that ring. And we'll label this vertical distance from the origin of the ring to a point along its axis as z. And note that this problem is also symmetric, because if we take a differential charge along the ring on one side, then we'll have the same differential charge on the other side, resulting in an electric field that points in this direction. So again, if we resolve these differential electric field vectors in the horizontal and vertical direction, the net electric field in the horizontal direction is going to be 0, because these will all cancel. So therefore our net electric field is going to act in the vertical direction. So we have 1 over 4 pi epsilon naught, and we're integrating with respect to the charge. So now given the charge is distributed along a circle, then we can write the differential charge as the linear charge density by this distance over here, which is the radius of the ring, d theta. And note that because we took the electric field component in the vertical direction, we need to resolve it in the vertical direction, so we'll take this angle of theta to do that. So taking cosine theta, we get z on r. So if we substitute for dq, we can take lambda and r outside the integral because they're constant. And we can also take z outside the integral because that's going to remain constant. So we have d theta on r squared, which using Pythagoras is z squared plus r squared. And then multiplying this by r, which is a square root of z squared plus r squared, we get this expression to the 3 on 2. And here we're integrating with respect to theta. So from theta equals 0 to 2 pi, given we have a circular ring. So given z and r are constant, we can take this expression outside the integral. So therefore the integral is evaluated to theta from 0 to 2 pi. So therefore we end up with the linear charge density by 2 pi r z. And this is the magnitude of our electric field. And the resulting electric field vector points in the vertical direction. Now note that we can make some analogies with a point charge. So the linear charge density multiplied by 2 pi r is going to give the net charge on that ring in coulombs. So therefore we can rewrite the magnitude of this electric field as q by z on 4 pi by the permittivity of free space. And let me remove this, by z squared plus r squared to the 3 on 2. So therefore where the distance to the point where we're determining the electric field is much larger than the radius of this ring, then this term becomes dominant and we can ignore this second term. So we end up with E is the charge by z on 4 pi epsilon naught, and z squared to the 3 on 2 is z cubed. And z on z cubed gives z squared in the denominator. So we can see that the thin ring behaves like a point charge at large distances from it. We can also determine the electric field at the center of a charged semicircular arc using integration. So if we take a differential charge along the arc, at the center of the arc, the electric field vector points radially and towards a negatively charged element. And on the other side, we have a similar vector, which we can again resolve in the horizontal direction and the vertical direction. So there's no net electric field in the horizontal direction due to symmetry. So if we take our angle theta as follows, our net electric field is going to point in the vertical direction, and our differential charge can be taken as the linear charge density by the arc length where this differential charge is distributed. So that will be r by the differential angle d theta. So lambda and r are going to be constants, so we take them out of the integral. So we have d theta on r squared, where r is the distance from this point to the differential charge, which is also constant. And we want the vertical component of the electric field, so we take sine theta. So simplifying this integral, we have lambda on 4 pi epsilon naught by r on r squared, which is r, and we're integrating from an angle of 0 to half of the arc being pi on 2. And therefore we multiply the result by 2 due to the symmetry of the problem. So in other words, the electric field, due to a differential charge on this side, is going to have the same magnitude. So we have sine theta d theta. So this integral evaluates a minus cosine theta from 0 to pi on 2. So it's going to evaluate to 1. And therefore we obtain lambda on 2 pi epsilon naught r. So this is the magnitude of the electric field at the center of the semicircular arc, and due to symmetry it acts upwards. Let's determine the electric field at a collinear point that's at some distance d from the end of the wire. So if we take our x direction as follows, and our differential element of charge, we can see that the electric field is going to point to the left, so radially from the charge. So what we have is the electric field in the horizontal direction is 1 on 4 pi epsilon naught, and our integral is as follows. So in this case our differential charge is the linear charge density by dx, and our radial distance from this differential charge to this point that's collinear with the wire is x plus d. So we can rewrite this integral as follows, taking lambda outside, which is constant. So we have dx on r squared. And we're integrating from x equals 0 to the length of the wire. So here we can use u substitution. So du is dx, and therefore our integral is written as follows. So that's going to evaluate to u to the minus 1 on minus 1, or minus 1 on u. And if we substitute back for u, we can rewrite our integral as follows. As minus 1 on x plus d, evaluated from 0 to L. So what we get is lambda on 4 pi epsilon naught minus 1 on L plus d. Then minus minus is a plus 1 on d. So you multiply the cross terms and add them together and divide by the product of the denominator. So that's going to give you the following result, being the linear charge density by L on 4 pi epsilon naught d by L plus d. So if we write this as the total charge on the wire, and where the distance from the wire to this point is much larger than the length of the wire, then we can write the electric field magnitude as Q over 4 pi epsilon naught d squared, because this term will dominate compared to this one. So the finite wire acts like a point charge, where the collinear point where we're determining the electric field is far from the wire.